In this section, we'll build a guitar digital effect pedal using Python. So I have loaded some libraries here. And first we will build this digital delay line using an array. So let's, just to recap, I told in the previous part that array has two parameters. One are the memory locations where the data is stored, and then are the addresses, and addresses are called as index. So we'll build this array and we will do a shift operation to see how this entire delay line functions. So let's define an array which is going from, say, 1 to 11 in steps of 1. So let's see how it looks. Here we are. So you can actually see we have an array here which is having number 1, 2, 3, 4, 5, 6, 7 till 10. And now we are going to see how to pick out numbers, store or retrieve numbers from this array using indexes. So let's say I need to retrieve this number, first number 1. So I know the index related to number 1 is 0. So this is how I'm going to read it. So remember, index is 0, and once I do this, number 1 has been retrieved here. That is from index 0, as you can see it from here. This is 0 index, and the first location of the array has been accessed. Similarly, if I need to retrieve the last number, so I know the index for the last number is -1, so I can use the same philosophy to retrieve the last number, and let's see what it is. It is number 10. So you can see that number 10 has been successfully retrieved. So we'll use this indexing system to store and retrieve data from this array. Now let's come to the shifting operation, which is the backbone of this delay. As I told you, with each clock tick, we are going to shift the numbers in this array, or shift the data inside this array, so that a delay effect is created. So how it can be done is like this. There's a function called mpRoll, and here I need to define what is my array. Where is my array? What's the name of the array? And 1 means that shift the data to right by 1 location. If I do it -1, then the shift will be towards left. So let's see what we get from here. So now you can see earlier my data was 1, 2, 3, 1, starting from 1 going to 10. Now number 10 has got popped out of this array and it has come to the first location, which means this entire array has shifted right. And this number 10 got popped out and got back into the first place. Let's run this entire operation in a loop so that you get a better understanding. So I'm going to loop through the entire length of the array, and what I'm saying is that I'll create another array called shifted array, which is taking the original array and shifting it by 1, that means right, and then I'm going to print this shifted array. Oh, so I have forgotten in range. So here we are. So now you can see that, this is to be indexed by I. So now we'll see that numbers are popping out from the right hand side and they're getting back into the queue. So number 9 has got popped out and it has come here. The number 8 has got popped out, it has come in the beginning. Then number 7 has got popped out of the array and it has come at the beginning of the array. So the numbers are getting shifted towards the right. With each clock tick, or with each run of this loop, the number gets shifted 1 position. So the clock is the basic unit, and the number of steps that are required to shift the array basically decides how much is going to be the delay. So we will see this entire thing in action. I hope you've understood how delay line is going to function in Python. So as I mentioned earlier, we will generate a guitar pluck, basically a decaying sinusoid at a frequency of 440 Hertz. 440 Hertz is the, in music, it's A note. And let's just first create this sample. So few parameters we have to set up front. So as I said earlier, since we have to, my idea is to generate audio signal out of it. So we will use the sampling rate of the sound card. So let's say my sampling rate is 44.1 kilohertz, which is how a typical sound card works. And then I have to decide how long is my signal, for what duration this signal is going to bring. So let's say it'll be there for, say, 6 seconds. And obviously this is in hertz. And I have to create a time axis so that I also need to plot it with respect to time to see how the signal is behaving. So let's say I create a variable t, and my time starts from 0. How long will it be? As long as there's the duration of the signal that I want. And how many number of such points do I need? Very simple. My sampling rate, which is fs, into duration of the signal. These many samples I need to create my entire time axis, and my endpoint, just to align it properly, I'm going to say my endpoint is going to be false. All right, so this has created t. If you're basically I've created this t here, and I'm going to create the rest of the signal now. So let's say as I said earlier, we're going to generate node A. So let's say node 8A has frequency 440 hertz. And then I had also mentioned that I need to create this entire expression, sine with exponential delay. So I now have created t, I have created f, and I'll create the rest of the input now. Let me call it as input signal. My input signal is nothing but a sine, which is 2 pi, so 2 pi into frequency into time. So this is my pure sinusoid, and it is supposed to decay exponentially. So now I'm going to create an exponential function, which is minus 10 into t. So here we are. I will now plot my input and see how does it look. So there's some plotting code here, which I've already coded here. So I'm just going to run this code now, and you can see the plot has appeared here. So you can see that I have this sinusoid, which is exponentially decaying, and my signal is of 6 seconds. My amplitude is plus minus 1, and this is what I'm going to use as input to my comb filter. If I zoom in, you can actually see the sinusoid inside it. So that can also be done. Let me just take a time slice of it. Let me just zoom into it so that you can see it. Here it is. So you can see there's a 440 hertz signal, which is tapering down in amplitude. So my input is working fine. Let me just now build the rest of the filter structure. So as mentioned earlier, I have to build this filter, and this filter has some parameters. For example, I have to specify what is the feedback, I have to specify how much is the delay, etc. So let's begin with specifying these delay parameters. So let's say my delay is 400 milliseconds. Delay in milliseconds is 400. This is obviously in milliseconds. And I need to know how this converts into the array size, delay buffer size. Basically, I know the time. I know that my samples have to be delayed by 400 milliseconds. So if once that is known, how big should be this buffer? Basically, now I'm trying to figure out what is the m here, and that will decide the size of the array, size of the delay buffer. So that's very simple. What I'm going to do is number of samples that are required, number of locations that are required in the delay line is nothing but my sampling frequency, my sampling rate multiplied by the delay that I'm looking for. So this is delay ms, and obviously it's in millisecond, and my sampling rate is in seconds. So I have to convert it back into seconds. And obviously this can be a floating number, so I have to convert it into an integer. Essentially what I'm doing is, since I have here said that I'm going to be sampling my signal at 44.1 kilohertz, that means every 1 second I'm generating 44.1 kilo samples. So that's in 1 second. So if I have to generate, if I have 400 milliseconds, then how many such samples will get created is defined by this particular equation here. Also, let me, and if you want to know what this number is, we can always print it out like so. My delay sample is 17640. Essentially what I've done here is I have figured out what should be the m, what should be the size of this array, based if given that 400 millisecond is what is required to be achieved. All right. So, and then I have to decide what should be my g. So as I said, my G should be attenuating the signal. So let's say my feedback or G is 0.5, and I also need to initialize this delay buffer. So what I can do is that let me call this whole structure as delay line, and delay line, and I know that I need to save 17,640 samples in this delay line. So I'm going to initialize it with all zeros. Basically, these are all placeholders in the delay line. The entire delay line is going to be initialized with the zeros. And how many such, what should be the size of this array? The size of the array is this delay samples. So now I have a delay line which is all filled with zeros. Basically, this delay has a size of 17,640 locations are inside this array, and as of now, before we start the algorithm, all of those data values are 0. Essentially, if you see here, all these numbers have become 0, and the size of this array is 17640. Okay, so moving on. Now we need to implement this function. So I have initialized my delay line. I have also requirement to store my output somewhere, my yn somewhere. So let me first define that output signal, and let me just make a placeholder for this output of my filter. And how many such, how big should be this array? This should be as big as my input is. So now I have a place to save my filter output. I have input signal, I have a delay buffer which is called as delay line. Everything is in place. Now I'm required to implement this structure. So what basically I'm going to implement is my input gets added with the with this feedback, which is gain multiplied by the output of this buffer. And how this buffer is working is that it is taking in the last value here. The last value of this buffer goes and gets multiplied by G, and then it gets added with the input. And then I have to shift out this array and replace this first value of the buffer with the current output. So let's see how we are going to implement this. So I'm going to loop through the entire input signal first, every sample of it. For I in range, however big my input signal is, I'm going to loop through all the samples. Okay, so that's my for loop has been set up to iterate through the entire input. What I'm going to do is I have to retrieve the last sample, the oldest sample in the delay line. So oldest sample in delay line is, if I'm shifting everything to right, so this will get filled first, then this, then this, then this, and this is going to be the latest sample, and this is going to be the oldest sample. And the index to the oldest sample is -1. This is what I need to retrieve from this location. So how I'm going to do is by using the index of that place. So let's say I'm going to retrieve my oldest sample, or rather oldest, say, delay sample, because it's coming from the delay line. And I have an array called delay line, and I'm accessing its last data point, which is last data point is indexed with -1. Okay. Now I am supposed to multiply this with the feedback and then add it back to the input signal. Essentially, what I have done here is this oldest delay sample is nothing but the output of this delay line, and this needs to get multiplied by the feedback, and then the whole thing should get added with the input. So how I'm going to do it is like this. So I had already initialized my output array, output signal, and I'm going to say that the current input, or rather input signal, my current input signal should get added with this expression, that is feedback multiplied by oldest delay sample. That's all there is to it. What I've done here is I've taken the last sample from this delay line, got it multiplied by G, and then whatever is the current sample that is coming from this side, it has got added with that. And one operation is now remaining, because now this oldest sample has been made use of. This has to be ejected out of the delay line and discarded, and whatever number is in the latest location, that latest location should store the current output. So the whole delay line is getting flushed out one by one with the oldest sample coming out from the side, and the freshest sample, which is going to be the current output, must get stored in this delay line. So how we are going to do it? I'm going to update this delay line by firstly shifting it right, as I had mentioned earlier. So my delay line must shift right. So the number has got flushed out. The number that I've already used, that is the oldest sample, has been flushed out. And now I'm going to access the first location of the delay line, which is the first location of delay line is indexed by 0. And what I'm going to feed it? Very simple. Whatever is the current output sample from the output, that must get stored in the first location of this array. So what is my output? My output signal. And what is the current sample? It is the ith sample. I have picked up the ith index from here. And where is it going to get stored? In the first location of the delay line. So effectively now this is acting like a delay line. Numbers enter from here, and with each clock tick, with each iteration of the loop, they start shifting towards this side, and then they keep getting multiplied by g and keep getting added with the input, and they keep coming out as output. All right. So let's see if this whole code is working. So I had already written some visualizations. Let's see if they're working. Okay, so basically I'm generating the plot for the input signal, time domain plot of the input signal, and time domain plot of the output signal. So with respect to time, this is the output signal, and with respect to time, this is the input signal. I've run the code, and obviously there's an error here, and error is okay. So this sign has got, yeah, this should fix it. This should fix it. Okay. Hopefully it should work now. No, G is not, obviously G is not defined because I had named it feedback. So it can't be G. I had declared this G as feedback. So this has to be corrected. Let's see. It is taking some time, and here we are. Brilliant. So this was my original signal, a decaying sinusoid. It ended till here. I've taken a replica of this, shrunk it in size, in amplitude, and attached it in front of the signal. And this is the first echo, this is the second echo, this is the third echo, this is the fourth echo, fifth, sixth, so on and so forth, until it decays down completely. And why it is decaying down is because of this factor, because of this G. It's less than 1, it's 0.5. So at some point of time, if this G is a large number, closer to 1, then these echoes will continue for a very, very long time, instead of 9 now. Also, I want to see the spectra of these plots, both input and output. So I had earlier written some code. Basically, I have taken the input signal. I have calculated its real valued FFT, and then I've taken the absolute value, the most positive value, to normalize this FFT. By normalization, I'm avoiding, because now I have to calculate the power in dB, and to do that I need to have a log function, and this log function cannot have a 0 value. To avoid that, I have normalized this signal and normalized this FFT, and I've created a frequency axis till my Nyquist frequency, and then I have gone on to do the same thing to output signal, and let's see if I'm able to generate the spectra. Excellent. So this is the input, and this is the spectrum of input. If you remember, my A note was at 440 Hertz, so there's a line spectra here. It clearly shows that in the input, there's a sinusoid which is ringing at 440 Hertz. And then I have this spectrum of this echo signal. And as you can see here, if I zoom into this part, these will all be ringing like comb kind of structures. And the spectrum has spread out because of this, because of the filter action. So far so good, but the real fun is to take these now signals, both input and output, convert them into sound file, maybe wave file, and see how they sound. And that will be the real test whether this filter is working or not. So for that, I had written some code earlier. Essentially, I am taking this input signal and converting it to a 16-bit number, 16-bit integer number suitable for conversion to wave.wave file. I'm giving this wave file a name, input signal.wave. The sample rate is 44.1 kilohertz, and then I'm going to save it save it in a location. Similarly, I'm going to do the exactly the same thing with the output. And then once these two wave files have got generated, I'm going to replay them using this command, display audio, at the rate, the same rate, that is 44.1 kilohertz. So let's see whether this is working or not. So here's a problem. So we have now two wave files. The first one is the input, and the second one is the output with delay. So let's see how they sound. So this is a 6-second signal, and as expected, it will start and it will die down after a while. And let's see how the delayed signal sounds. Clearly, you can hear echoes. So I hope you enjoyed this demonstration of guitar delay effect implementation in Python. This is just the start point. Many things are added onto this signal processing chain. For example, low pass filters and impulse response of the room to create reverb, etc. We will try to cover those topics later in subsequent video series. Thank you so much.